So, when we are introduced to the physics of flight in school, we're often shown something like this. A picture of an airplane with 4 arrows going left, right, up, and down, representing the basic forces of thrust, drag, lift, and weight respectively. The causes of 3 of these forces are pretty clear. Thrust comes from the engines, drag comes from friction and aerodynamics, and weight comes from one too many free peanuts. Just kidding, it's gravity. But lift, the 4th force, is often incorrectly explained as emerging from a process that sounds something like this. Because of the shape of the wing, a packet of air flowing over the top must travel faster in order to meet up with its bottom traversing counterpart. Because the air moves faster, via Bernoulli's principle, the area above the wing has a lower pressure, and therefore the higher pressure under the wing pushes the plane up. But this doesn't make any sense. Why do 2 packets of air care whether or not they meet up with each other? And if they don't, how do we explain lift? Well, let's start with the shape of a standard wing from the side. We can see here that the wing is sitting at a slight upwards angle relative to the horizon. This is called the angle of attack. A common, more correct explanation uses Newton's third law, the whole thing about equal and opposite reactions, to propose that since more air hits the bottom of the wing, which faces more of the oncoming streamlines due to the angle of attack, the craft is pushed upwards and slightly backwards. Minute Physics has a video explaining this a bit more in depth, so I'll just link it here, but this is why most commercial airliners you'll fly in keep the plane pitched about 2 degrees above the horizon instead of completely level. But this explanation, while commonly used, is not the complete picture. It's one part of the puzzle, but to call ourselves Jigsaw, we have to study the... Well, to explain the Kutta-Joukowsky theorem, we first need to acknowledge that air is a fluid, but still not a liquid, and somewhat viscous. It likes to stick to itself. Also, due to the various properties of air and fluids in general, air traveling underneath the wing will initially get pulled around the trailing edge and in the direction of the top side of the wing as the plane begins to take off. Because air is viscous and pulls nearby packets alongside it, a starting vortex is created, which is trying to make the air it is composed of move in a circular direction. In comes Lord Kelvin, that one, with his circulation theorem, which basically states that the net circulation of a fluid is independent of time. In other words, if we start out with a scenario with no circulation around the wings, like, say, a plane sitting on a runway, and produce a starting vortex by moving down the runway, then another vortex called a bound vortex with equal strength but opposite direction has to form somewhere. In the case of our wings, the bound vortex will actually encircle the top and bottom of the wing. Therefore, air flowing over the wing will be accelerated with the direction of the bound vortex, which does, via Bernoulli's principle, decrease the pressure above the wing. The bound vortex also makes it so that both the upper and lower streams passing over the wing meet at the trailing edge and not just near it on the top side like our starting scenario. This is known as the Kutta condition, and every time the plane changes its speed or angle of attack, the Kutta condition is essentially reset and the starting vortex forms again. After the condition is met, the starting vortex is then shed downstream in the wake of the aircraft while the bound vortex remains bound, to the wing. So, while both Newtonian physics and fluid dynamics can be used to explain how a plane achieves lift, you really need both of them together to get the bigger picture. In fact, the shape of the vast majority of aircraft wings can be attributed to Kutta and Joukowsky's work. Anyways, that's it for now, and remember, even if you feel alone in this world, you might just be a starting vortex waiting for a bound vortex to form around your airfoil. Or not.